the live stream now. Okay, so I think we'll get started in a couple of minutes. Okay, there's my window. That's good. Okay, I think I fixed the echo issue. Yeah, I think people, other hosts should keep admitting students as they enter Zoom. I don't know how to turn off my notifications that come up telling me that they're waiting people. Anyway. Okay, I think let's get started. Welcome everyone for the third lecture of digital design and computer architecture. If you remember, we were talking about some mysteries in computer architecture, and we're going to continue that today and hopefully finish the mysteries. And then Hassan will give an introduction to the FPGAs and the labs, basically the hands-on assignments that you will do during this semester, which is going to be fun. It's going to be the very practical aspects of this course. As I mentioned, we're going to do a lot of conceptual thinking during the lectures, cover trade-offs, but you will get a chance to do the practical aspects during the labs. But today, we'll have a little bit more fun before we really start with the core material and start building up from the transistor bottom up into how a computer works. But let's have some more fun today to understand how what we're going to do really affects computers. And I'm going to also start from the bottom up today also actually in some of these mysteries. Okay, so remember we were continuing to talk about some mysteries and we covered Meltdown and Spectre. We're going to cover refresh and memory performance attacks. I could actually add more over here. There are many, many more mysteries, both in the workings of computer architectures as well as performance and energy issues, as well as reliability and security issues, but we don't have time. There are too many stories to be told. But I think I selected these stories because these stories are actually quite interesting, I think, and they've had significant impact on how things are happening in computing system design today. Okay, just to jog your memory, we talked about Meltdown and Spectre. If you didn't attend the last lecture, you can go and find it online and attend it. And we talked about how Meltdown and Spectre span across the hierarchy, and the solution space goes all the way from logic to potentially algorithms, actually. And we also mentioned that two major goals of this course is to enable you to think critically so that you can question everything, hopefully. That's how progress happens, actually, by questioning things as opposed to by accepting things as they are, right? That's the fundamental definition of progress. If you don't question, you lose in the progress. And also enable you to think broadly. I think this is different because you can solve the problems, for example, in potentially one layer over here that I showed you, but I would like to hopefully enable you to think more broadly than just one layer, not just logic, not just system software, not just algorithm, but hopefully you can think about the solution space and trade-offs across multiple layers as we've been discussing. Okay, so we're going to see more of that today, but let me quickly also jog your memory on the second mystery that we talked about, RowHammer, and we talked about this multiple times, so I'm not going to mention it again, except to show you some slides so that you can jog your memory, if you will. And if you're really interested, as I mentioned, you can actually go and watch this state-of-the-art lecture, let's say, on RowHammer, which was delivered almost last month. Okay, now let's jump into something else. We're going to actually still talk about main memory, which I mentioned in the first lecture is a huge bottleneck today. That's why actually we're going to talk about it a lot. But a very different aspect of main memory, which is refresh. Basically, today's main memories are built using dynamic random access memory technology, which was developed in the 1960s. The first patent on it is from 1965, Bob Denard, actually. And this memory technology is great, actually, because clearly it's been around for more than 50 years, right? And whenever you buy memory sticks, you buy dynamic random access memory today. So it's been extremely successful, as you can see. But it has some fundamental issues also. And one of the fundamental issues is refresh. And this refresh problem is actually becoming much worse going into the future, just like the RowHammer problem. And these two issues are actually going to bottleneck how far we can scale the size of this technology into the future, in my opinion. And let me cover this one because this is fun. So if you look at memory in the system, this is an old picture of a multi-core system. This is AMD Barcelona, which was around 2004 or 2006 or so, let's say. And you can see that this is the core chip, the CPU chip. It has multiple cores. We're going to talk about that later on also. It is a bunch of on-chip memory called caches. And we're going to talk about that also. Some of them are shared, some of them are not shared. We're going to talk about that as well. And then there's a memory controller, and then there's a DRAM interface. And this is the DRAM chip or module, let's say, which consists of many DRAM chips. So we're going to talk about DRAM toward the end of this course. We're going to build up to it, but fundamentally, it's going to be similar to some of the other memories we see earlier, but it will have this refresh problem. So if you look at what a DRAM cell looks like, let's do bottom up right now. This was the top down view of what DRAM looks like. Now, if you actually zoom in into a chip, and if you actually zoom into a single cell that stores a single bit of data, it looks like this, basically. Basically, a DRAM cell consists of a capacitor. This is the capacitor over here, and an access transistor here. And you can see that the data is stored in this this capacitor, sorry. And the access transistor is used to actually access this data. So basically, the data is stored in the capacitor in terms of charge. And you need to be able to actually access that charge. With the presence of charge indicates a 1, let's say. The absence of charge indicates a 0. That's, of course, an encoding issue. I hear some, well, I see some chat. Maybe TAs can handle the questions in the chat. Are there issues with audio quality? Can someone speak up? Can you hear me well, or?
The voice is a bit cracky.
Oh, okay. Is it better now, or? I wonder why that is.
A bit, yeah.
It's a bit better.
Yeah.
Okay, let me see. Let me see actually my choices. Okay, this is actually the better microphone, but let me move the microphone a little bit further. Is this better? Okay, I didn't understand that one. So I wonder why that is.
For me, it's like just overdriving a lot.
Okay, interesting. Interesting. Okay. So somebody says it's good though. So I moved the microphone a little bit further away from me. Is this better? Anyone? Okay, I see a lot of yeses. So maybe the microphone moved further down. That's probably the reason. Sorry about that. Yeah, please let me know when that happens. I don't always monitor the chat. Okay. Yeah, it looks a bit funny. I agree. Okay, so basically, let me go back. DRAM cell stores charge in the capacitor, and that charge represents your data, 1 or 0, basically. And you have many of these DRAM cells. This is just 1 bit, right? If you basically actually have many rows of such cells, and each row is actually, let's say, 8 kilobytes, and you have thousands and thousands and thousands of rows in a chip. Now, one problem with this capacitor is this capacitor charge leaks over time through the access transistor I showed you. And the memory controller needs to refresh each row periodically to restore the charge, because you've written some data into your DRAM and you don't want to lose it, obviously. So periodically you need to refresh it before the charge actually leaks to a point that you have lost the data. Basically, you never want to get to the point that you have lost too much charge from these cells, right? That's what makes sense. So this is the fundamental limitation of the technology. That's why this is called dynamic random access memory. You dynamically need to refresh it. Basically, you need to, what does refresh mean? It means that you need to activate every row every n milliseconds. And typical n today is 64 milliseconds. I say typical because this is going down actually. In some chips, it's 32 milliseconds, for example, in LPDDR chips. At high temperatures, it's actually lower, 16 milliseconds, for example, in some LPDDR chips. So basically, at higher temperatures, the charge leaks faster. So at higher temperatures, you actually need to refresh even more. Okay, so clearly there are downsides of refresh, right? If you're doing a refresh, that means you need to activate each row. Remember the activates when we talked about RowHammer, it takes time. And then you need to also pre-charge the row. So you need to actually access the row once, let's say. So this consumes energy to retain the data. This consumes performance degradation because while you're refreshing a bank, let's say, or a DRAM module, it's unavailable. You cannot do accesses to it. So the processor cannot actually service the data that the user wants to access. So that's unfortunate, just to maintain the data. This also has impact on quality of service or predictability. While the computer is refreshing memory, for example, you may have long pause times depending on how this refresh happens and how frequently it happens. And a critical request, for example, that the user really wants at that time may be delayed because you have to refresh the bank, right? And that's actually unfortunate in terms of quality of service. And it turns out how frequently you need to do refresh really limits how far into the future you can scale the capacity of DRAM. Let me actually talk about this a little bit. Basically, today's DRAM chips consist of some number of bits, let's say 8 gigabits. If you want to make this like 64 gigabits, then it becomes harder because refresh becomes a bottleneck. That's what this last bullet over here means. Refresh rate limits DRAM capacity scaling. And I'm going to actually show you some examples over here. Okay, let's give you some examples. So imagine a system with 1 exabyte DRAM. I'm going to just make it up to the 60 bytes. And in fact, supercomputers actually have this. Well, almost have this. They're going to have this if they don't have it today. So certainly they were at petabytes recently. I don't think they've reached exabytes yet, but I see no reason why they will not reach it. And assume a row size of 8 kilobytes to the 13 bytes. So of course, first question is easy. How many rows are there? You divide the memory size with the row size. Basically, you get 2 to the 47, right? That's a lot actually. And how many refreshes happen in 64 milliseconds? That's essentially 2 to the 47 rows need to be refreshed every 64 milliseconds, assuming that every row needs to be refreshed every 64 milliseconds. What is the total power consumption of DRAM refresh? I'm not going to answer this. This is going to be a brownie point question for you. You can take a look at it. In fact, you can find and do the calculations online. And then once you figure out what is the total power consumption in terms of watts, let's say, you can figure out what is the total energy consumption of DRAM refresh during one day in a system like this. And you'll be surprised that it's going to be a lot actually, because this is going to be on the order of kilowatts, let's say, the power consumption. And energy is really a function of power over time, right? And this is really constant power that's consumed at a given point in time, because you have to refresh every row at the same frequency as we discussed. So this is a good exercise. I will mention that this is an optional homework. You'll get brownie points from me if you do it. And at some point, we may give you extra credit also, but currently not. But in the past, people have done it for fun and sent me emails. I'm happy to receive those emails. It's always good to see people looking into this. This is not a hard task. You just need to figure out. Essentially what is the power consumption of a single DRAM refresh, right? Once you figure that out, it's a simple multiplication, right? Okay, and the refresh power, if it keeps increasing, then you have a problem, of course. That value, all of the values that we compute based on the questions on the slide will keep increasing. Okay, so now let me give you some example overheads that we have calculated based on our research. So this is a bit old research. You can see that this is ISCA 2012. Today, actually, we have DRAM chips that have 16 gigabit capacity, I believe. At the time, the largest DRAM chips had 8 gigabits, meaning 8 billion of these cells that I showed you earlier. And this is the percentage of time spent refreshing. So at the time, with a 4 gigabit common DRAM chip, it was about 8%, which is not bad potentially, but it's still close to 10%, right? It's not good also. But if you actually kept things as they are, if you keep adding DRAM cells and without doing anything about the refresh problem, if you want to build a 64 gigabit DRAM chip, refreshes would consume about 46% of the time. Meaning you're building this device, the DRAM chip, so that you can access memory, but 46% of the time you cannot access the memory because memory needs to maintain the data by refreshing. Now, this doesn't sound good, right? Basically, the throughput, half of the throughput of the DRAM chip is wasted on refresh. So clearly, we don't want to. This is not an efficient system, let's say. Okay, now let's take a look at the energy overhead. This is the energy overhead while you're accessing DRAM, and this depends on, of course, how much energy you're spending on accessing versus not accessing. Because if you're not accessing DRAM, for example, my cell phone right now, I'm not using it. It needs to maintain data inside its DRAM. It doesn't, basically it puts DRAM to a mode called self-refresh. All what the DRAM is doing is maintaining data right now. So most of the DRAM energy is spent on maintenance of the data, meaning refresh. But if you're accessing DRAM, some part of the energy is spent on access, some part of the energy is spent on maintaining data. And it turns out, sorry about that, my computer has a mind of its own, it moved. But basically, if you, basically for a 4 gigabit device, about 15% of the DRAM energy is spent on refreshing. But in the future, if you don't do anything about this problem, if you keep scaling the size of DRAM, then about 47% of the time, 47% of the energy would be spent on refreshing. So essentially, this is a scalability problem, because if you don't do anything about this problem, and if you keep adding cells to memory, rows to memory, so that you can increase the capacity, half of the performance will be lost and half of the energy will be lost just to maintain data with the refresh. That's why this is a big scaling problem. Okay. So I've given you the problem. I'm not going to talk a whole lot about solutions, but I'm going to give you some solution directions. And we're going to talk about one potential solution, which has a significant impact in the field, actually. So, okay, basically, one observation is that today we're refreshing every DRAM row every 64 milliseconds. Right. Actually, today in some chips, it's every 32 milliseconds. It's gone down. It's become much worse, basically. Okay, critical thinking says, do we really need to do that, basically? If you look at the problem fresh, let's say, if you're a critical thinker, you should always question these things. Do we really need to do this? And once you ask this question, you may actually come up with many, many different answers. One answer I will show you will be, no, we don't, because not every row needs to be, some rows can retain data for much longer by nature. Or you can come up with the answer that no, because some rows don't store data that I care about, right? I'm not going to talk about that, but that could be another answer, right? Or someone can come up with an answer, no, because I can, in my operating system or in my application, I can guarantee that I'm not going to use a row for more than 64 milliseconds. Of course, this may be harder, but now you can start imagining new ideas, right? And if you can somehow guarantee what I just said, then maybe you don't need to refresh DRAM at all, right? Of course, that's a difficult guarantee to do. I'm not suggesting it's easy, but once you start doing this critical thinking, you can come up with new ideas to solve the problem. Okay, now let me go into one potential idea, basically. What if we knew what happened underneath inside the DRAM chip and expose that information to upper layers? Basically, what happened for each DRAM row or DRAM cell, let's say. Okay, so let's take a look at underneath. This is a retention time, data retention time profile of DRAM. So you can represent DRAM as a set of cells. Let's say in an 8 gigabit DRAM chip, you have 8 billion of these bits. And it turns out, if you do some experiments, you'll figure out that this is the retention time, data retention time of DRAM cells. Basically, an overwhelming majority of DRAM cells can retain data for more than 256 milliseconds. There's a very small fraction of cells that have to be refreshed every 64 milliseconds because they cannot retain data for more than 128 milliseconds. And there's a little larger fraction of DRAM cells have to be refreshed every 128 milliseconds because they retain data somewhere between these two values, 128 to 256 milliseconds. Now, if you know this information or figure it out somehow, that's great. Then you can build a memory controller that dynamically adjusts the refresh rate based on which row these cells are in. So that's the idea, basically. So that's the beauty of this, right? Now you understand now you have one more insight to the underlying circuitry and how it's behaved. Okay, so now the next question could be, why do we have such a profile? I figured out after a lot of testing that this is the case. But why is this the case? And the answer is manufacturing is not perfect. Basically, manufacturing, nothing is perfect, and DRAM is not nothing. DRAM is not something different. It's manufactured, right? And it has devices that are vulnerable to variation in manufacturing. So because of manufacturing variation, not all DRAM cells are exactly the same. Not all capacitors are the same. Not all transistors are the same. Not all wires are the same. As a result, some cells and capacitors are more leakier than others, whereas some are much less leaky than others. And this is called essentially manufacturing process variation. And this exists in all components you build. Certainly electronic components, but also non-electronic components also, right? This chair that I have over here that you don't see is not exactly the same as this other chair that is next to it, even though they clearly were manufactured at the same time, right? Basically, there's some variation between the chairs. And variation is true for other things as well, like electronic components, as we see. And this is the reason why we have the profile that I showed you earlier over here. You see? Okay. Okay, there are some questions on the chat, so I will recommend people to answer it, but let's take a look very quickly. Okay, I think people are answering it. That's good. So somebody says, how is it going from 0 to 1 if you lose voltage? So, okay, 0 to 1, that's a good question. So you always lose charge. Basically, you have some charge stored inside the capacitor, and you represent the charge value as a 1 or 0. But you don't have to do that, right? You can represent the charge value as a 0 and non-charge value as 1, right? So basically, the logical value change is different from the charge loss. So if you don't refresh, you lose charge, but the effect on the logical value that's stored in the cell is dependent on how you represent a charged value in terms of a bit or not, right? So keep that in mind. We will get back to that. Okay, so somebody says, why do we need to refresh more often if the number of cells grows? Because you have more cells. So there are two reasons why you need to refresh more often as you scale the technology node going into the future. First of all, if you want to have a 64 gigabit chip, you have to have many, many more rows. So you need to refresh more rows. And the second is you need to reduce the size of the cell. That's how you can cram more cells in a given chip. And once you reduce the size of the cell, cells become leakier, and you need to refresh every single cell more often also. Okay, I see people developing ideas. That's good. Couldn't we map which cells are mismanufactured and not use them? So that could be another solution, basically. If you know this information, basically, so you've just developed another solution based on knowing what's going on underneath, right? You can basically say, operating system, I know which cells are need to be refreshed, let's say, more frequently than 256 milliseconds. I'm going to tell you which ones those are, never allocate data on them, and I'm going to refresh my memory every 256 milliseconds. You can do that, yes, as long as you make sure that no one allocates data into those cells, right? So that's the idea. So good people are developing ideas, and that's exactly the purpose of this lecture right now. If you know what's going on underneath, then you can solve the problems, and you can develop many, many ideas. Okay, so let me give you the idea that I was going to give you, basically. So how do we take advantage of this profile? Assume we know the retention time of each row exactly. What can we do with this information? Who do we expose this information to? How much information do we expose? Because that really affects our overhead in terms of how much information we store, how much power we consume in communicating that information, how much verification complexity and cost we have to actually find out that information perfectly, etc. How do we determine this profile information is another question, actually. Also, who determines it? In fact, it turns out this is the most difficult part here. How do you determine this profile information? And when we started this research, we basically assumed that this profile information is available. And then we said, okay, if this profile information is somehow magically available to you correctly, this is what you can do with it. And I'm going to explain that. But how do you actually make sure this profile information is correctly available to you is a completely different research question. And that requires a lot of work, actually, because it turns out this profile is not easy to find out, because it turns out DRAM cells sometimes change their retention times dynamically. For example, if you look at a DRAM cell right now, if you observe it right now, it may retain data for 100 seconds. And that's true, actually. There are some DRAM cells that can retain data for 100 seconds. But later, let's say 1 day later, you test this DRAM cell and you check how long it retains data. It may retain data for only 16 milliseconds. So this is a problem called variable retention time problem. And I like thinking of it as quantum-like effects in modern circuitry, because it's like a quantum-like effect, basically. It's not predictable. This process is random. And randomly, a cell's retention time changes. Of course, now if this is happening, how do you figure out this profile? Now, we have developed a lot of methods to figure this out. I'm not going to tell you about those. Those are much more advanced. For now, assume that this profile is correct, but even getting this profile is actually very, 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 very interesting. Okay, so basically, this is really a problem that spans across the stack again. As I said earlier, it even can go to your algorithm. You can say, in my algorithms, I'm going to ensure that I'm never going to need a piece of data for longer than 64 milliseconds. And if you can somehow ensure that magically, of course, magic is dependent on how you do it. Clearly, it's not magic. It has to be a real mechanism. If you can somehow ensure that, then you can get rid of refresh. You can have a refresh-free memory system, right? And you can actually get rid of a lot of overhead in your system. Okay, somebody says this profile information must be stored somewhere. So this problem might also occur. So that's a very good question. And yes, you need to be careful about that. I'm going to talk about that storage a little bit. We're not going to go into a lot of detail, but yes, you need to make sure that you don't lose the data or metadata that stores this information about this profile. Very good. Okay, so let me go into the solution a little bit more, at least the solution that we have proposed. Basically, this is real data from real DRAM chips. And the observation is overwhelming majority of DRAM rows can be refreshed much less often without losing data. So let's take a look at this data. So this graph shows on the x-axis the refresh interval, how often you refresh, basically. This is 64 milliseconds, as you can see. So assuming that you refresh every 64 milliseconds, you should not get any errors. So y-axis is cumulative cell failure probability. And that's the left y-axis. And the right y-axis is really the same axis, but represented in number of cells that have errors in 32 gigabytes of DRAM. So at 64 milliseconds, you should really get 0 cells that have failures, or close to 0 cells. There's some inherent failure rate that may happen, but anyway, we're not going to talk about that. So if you actually refresh every 128 milliseconds, basically get rid of half of your refreshes, if you can think of it that way, only 30 cells will have errors. If you halve your refresh rate a little bit more, refresh every 256 milliseconds, then only 1,000 cells fail. So it's not that many cells, basically. So you can actually use solutions like your fellow student mentioned, right? So the question is, can we exploit this to reduce refresh operations at low cost? And the answer is yes. I'm going to give you one answer. I've already given you basically only about 1,000 rows and 32 gigabyte DRAM need refresh every 64 milliseconds. But today we refresh all rows every 64 milliseconds. This is a huge inefficiency. And the key idea of the mechanism, which we call RAIDER, retention-aware intelligent DRAM refresh, is to refresh weak rows more frequently, all other rows less frequently. So let me tell you the key idea, basically. The mechanism consists of 3 steps, and it's all based on the assumption that we have this profile. So first, you need to profile and get that profile. Identify the retention time of all DRAM rows. This can be done at different times, design time, or during operation even. You can incrementally figure out the retention time of DRAM rows and store them somewhere. And the second is binning. You can store rows into bins by retention time. And for that, we're going to use a data structure called Bloom filters, which I hopefully will get to describe to you at the end of this lecture if we have time. Otherwise, I will refer you to another lecture, but this is important, I think, so I'll try to get to that. So basically, we're going to look at DRAM. We're going to profile and find out this information that I've mentioned, and we're going to store this information in a compact way, such that we represent which rows are in which set. And there are 3 sets of rows. Rows that need to be refreshed every 64 milliseconds, rows that need to be refreshed every 128 milliseconds, and rows that need to be refreshed every 256 milliseconds, right? So if you represent these sets nicely, cleanly, with very small hardware overhead, you can actually have very little overhead. And it turns out we can represent this information with only 1.25 kilobyte storage in the memory controller for a large main memory size. And then the third step is memory controller consults this information, how often each row needs to be refreshed, and refreshes rows in different bins at different rates. So it needs to check the bins to determine the refresh rate of a row. So these 3 steps are easily implementable, actually, except for the first one. First one is the hard one. How do you profile and figure it out? I'm not going to talk about that. But if you actually do this, if you actually do all of this, you get significant benefits. So let me give you some simulation results. So clearly this system is not designed. It requires a lot of work to actually design it. So a lot of what we do in computer architecture is to test the ideas first in simulation. Like what you will do in your labs also, actually. You will simulate your designs to figure out whether they're functional, or whether their performance is reaching some clock frequency, for example. So we did a higher level simulation in this work. Basically, we assumed a system with 32 GB DRAM, multiple cores, as you can see, various workloads. And we basically designed the hardware carefully so that we have 2 Bloom filters, some hardware cost, as you can see. And it turns out you can reduce the refreshes by almost 75%. And this should be obvious to you because what we're doing is most DRAM cells are being refreshed at 1/4 the rate. As a result, you should really get somewhere close to 25% of the original refreshes, meaning that you're reducing the refreshes by 75%. There are only some number of refreshes that you do in a smaller fraction that eats away from the 75%. So this is great, right? Basically, you're getting 3/4 of the refreshes. Now, this turns out it leads to a significant DRAM energy reduction, like 16% dynamic. Now, if your DRAM is not working, you get even higher power reductions. So, for example, in my cell phone, DRAM is wasting a lot of power. I get 20% reductions over there. Okay, and the performance improvement is also significant. It's almost about 10%, basically, with very little hardware cost in the end. Okay, and also, as I mentioned, this is a scalability problem, meaning that in the future, this sort of idea should become better. And that's exactly what we tested in these figures over here. If you look to the left figure over here, this is device capacity on the left on the x-axis, and the energy per access on the y-axis. And auto is the baseline, and radar is the solution that I described. You can see that in a 4 gigabit chip, you save 16% of energy, but in a 64 gigabit chip, you save 50% of energy. So basically, the benefits becomes higher in a larger chip because in a larger chip, you're doing many more refreshes, and still a large fraction of them are not necessary. And you can see the performance improvement over here. Performance improvement becomes even better, actually, as you go from 4 gigabit chips. And the performance improvement is like minimal, 10%, let's say. But with 64 gigabit chip, it's about 100%. This is because refreshes are actually really backing up a lot of requests that you really want to do in the end. And with a 64 gigabit DRAM chip, you save a lot more in terms of performance. Okay, there are 2 questions I will try to handle. I really wonder if this kind of profiling has to be updated frequently. So not all of it, but some of it needs to be updated frequently because of this variable retention time problem, the quantum-like effects that I mentioned, where your retention time changes. So you need to have some dynamic capability to update the profile. So that's a very good question, actually. Doesn't this also affect the lifetime of the cells? That's also a very good question, actually. So it turns out lifetime in DRAM is not that problematic. In the future, we may have more problems with lifetime, but as far as we know, lifetime, today we don't need to worry that much about the lifetime of cells in DRAM. So it doesn't go bad that quickly. Now, nobody knows what the implications are 30 years down the road. So we need to think about the 30 years down the road, but within 5 years, 6 years, it's not a huge problem, let's say. Okay. Okay, so let me go into the takeaway. So we've covered another mystery, let's say. Hopefully it's not a mystery anymore to you. This refresh problem is not a mystery, I think, but now that we've covered it. Basically, my takeaway again is breaking the abstraction layers between components and transformation hierarchy levels and knowing what is underneath enables you to understand and solve problems. And this is one problem, basically, as you can see. If you really want to design a better energy efficient system, you need to know what's going on underneath. And this is, again, it could be hardware software cooperative. Some of the solutions proposed by your fellow students who said that, okay, make sure that these DRAM rows are not used. That's a perfectly valid solution, but that requires cooperation from the operating system and potentially application as well, right? Okay, so if you're really interested in more reading, I would recommend looking into this Radar paper. And we actually have a lot of work in DRAM refresh, which I'm not going to mention over here, but you can, if you're really interested, you can go and watch some of the videos. And this is one of the videos that we cover in the more advanced class. In more advanced class, we actually go more into the data retention problem, not just in DRAM, but also in SSDs. Because in SSDs, actually, data retention problems can be much, much worse, as you will see in those lectures. Okay, so now we're done with this mystery. Let's go into some other mystery, which is the memory performance attacks. And if you have time at the end, I will cover Bloom filters, and I would really like to cover Bloom filters because I think you can actually benefit a lot from Bloom filters, but let's see. Okay, so memory performance attacks, I'm going to show you the same picture, multi-core systems. We're going to look at an issue related to multi-core systems, but it's really an issue related to any system where memory is shared between multiple different devices. So multi-core systems consist of cores that can execute independent applications, and each core has some cache, L1 cache, and a private L2 cache, and then they share L3 caches, let's say. Sometimes there are L4 caches, etc. And then there's a memory controller. If you miss in all of those caches, the request goes to the memory controller, and then you need to access the DRAM interface, and then you access the DRAM banks, as we discussed earlier. Now, if you were taking this class like 25 years ago, we would not be talking about many multi-core because there would not be multi-core. There used to be a single core, right? And people tried to scale the performance of that single core, and they said this is too hard. There are a lot of good ideas to scale the performance, but the energy and complexity increases significantly. So at some point, the industry decided to, instead of increasing the core performance a lot or dedicating all of the transistors in a single chip to a single core, they said, okay, we're going to dedicate these transistors to multiple of these processing cores. Now they're building multiple cores, basically, many cores, let's say. And the idea is each core is simpler and lower power than a single large core that would otherwise occupy the entire chip. And this also enables an opportunity, which is parallel processing on a single chip, right? Now you can actually partition your program across the cores or have multiple programs running independently across the different cores. Now it can actually be much faster or have higher throughput. You can have newer applications. And these are some example multi-core engines that are relatively old right now. But you can see Sun Niagara actually was one of the first multi-core engines. Also IBM Power 4, which is not in this slide actually. This is Sun Niagara 2. You can see that there are 8 cores over here. AMD has 4 cores. There are 8 cores over here. This is a heterogeneous multi-core system IBM sell with 8 plus 1 cores. One core is different from the others. And there are other systems, as you can see over here. NVIDIA Fermi is a GPU that has different kind of cores. Sometimes cores are advertised differently, of course, in different domains, depending on how much money you want to make. But in this case, we're going to take core as an engine that can execute a single program, let's say. So, okay, if you want to put many cores on a chip, what you really want is scalable performance with the number of cores. What does that mean? If you put n cores into the chip, you want n times the system performance compared to 1 core, right? And that's reasonable, right? Ideally, this is called linear scaling. You want to get this linear scalability curve. Now, what you get today is unfortunately something completely different. So these are actually results that we generated on real systems about like 14, 15 years ago right now. But I think you can generate similar results, although things have become better, but maybe not as good as what we wanted them to be. So basically, if you run 2 applications on a 2-core system, dual-core system, MATLAB and GCC, these are both popular applications. And you could be running them together in cloud, for example, or on your computer, because you're using both of these applications, right? And that's the benefit of multi-core. You should really get high throughput by running 2 applications. And if you measure the slowdown each application experiences compared to when it's run alone on the system by itself, on the same system, this is what you get. So MATLAB, when they're running together, MATLAB slows down by 7% only compared to when it's run alone on the system. And GCC slows down by 3x. Now, that's a huge difference. Now, immediately you say, this looks unfair, and that's certainly true. But also it's low performance because now GCC is not getting a lot of performance. If it were running alone, it would have run 3x faster. Now, somehow MATLAB is hogging the resources, right? Okay, so you go and say, oh, maybe I did something wrong in the operating system. Operating system is somehow is not scheduling GCC or not prioritizing GCC. And you go and in your operating system, favorite operating system, you basically change the priority and make MATLAB low priority and make GCC high priority, and nothing changes, which indicates that it's not an operating system level problem. Okay, so we call this a memory performance log. So let me tell you what's happening after asking you 3 questions, 3 rhetorical questions again. Can you figure out why the applications slow down if you do not know the underlying system and how it works? An answer would be no, I think. Of course, you need to do experiments and figure out what's going on, but you need to know something to be able to do the experiments. Can you figure out why there's a disparity in slowdowns if you do not know how the system executes the programs? Again, my answer would be no over here. And can you fix the problem without knowing what is happening underneath? And my answer again would be no over here. And this can cause a lot of inefficiency, actually. Let's go back to this picture. People may be running a lot of workloads in their data centers, and this may be happening. They may not even know that this may be happening. And as a result, there might be a lot of inefficiency in the system. And inefficiency always leads to energy waste. Even though it's not quantified here, this sort of inefficiency always leads to energy waste. And it also always actually leads to some sustainability problems. Today, we have a huge problem with sustainability in the world, not just in computing, but computing is increasingly a larger fraction of the things that contribute to the sustainability problem. And if we keep designing inefficient systems that look like this, and if you don't even know that the systems are inefficient, and if you don't do anything about it, we're just going to exacerbate the problem. And all of the problems that we're facing, like climate, is going to get worse, basically. So that's the bigger importance of the problem, if you will. If you don't buy that this is a problem, this is really a problem, actually. Okay, so the other three questions basically reworded. Why is there any slowdown? Why is there a disparity in slowdowns? How can we solve the problem if you do not want that disparity? So one of your students said thermal throttling. That's a great, actually, conjecture, let's say. In this case, it was not thermal throttling. You're right, it could be thermal throttling. It could be that, so modern systems, what they do is, when they figure out that the system is getting close to a thermal emergency, let's say, if it's running at a temperature that's that is considered too high, that it would potentially break down the system, modern systems do automatic throttling of workloads such that they slow the workloads, like slow the clock frequency and reduce the voltage of a core. Now, this could be due to thermal throttling. It's not in this case, because we actually verified that that's not the case. These workloads are running in nice temperature, let's say. And also, if it were due to thermal throttling, it's a very unfair way of throttling the system, I would say. It's really doing a bad job and throttling one core only and penalizing one core. But it's very good. I like the fact that you all are thinking critically right now and trying to understand what's going on. So somebody says RAM bottleneck, and we're going to get to that. It's in the end, yes, it's going to be a memory bottleneck. Okay, so how can we solve the problem? What do we want, basically, the system to provide? So you need to answer that also when you solve the problem. Okay, why is this important? I think I gave you the importance of this, but let me cover this a little bit more. Basically, we want to execute applications in parallel in multi-core systems, consolidate more and more, put more and more efficiently in cloud computing mobile phones. And we want to mix different types of applications together, those requiring quality of service guarantees, for example, pedestrian detection in a self-driving car, and something else in a self-driving car. You collocate them for some reason so that you can actually improve efficiency. You don't have all the resources in the world, right? But then there may be others that are important, but less so, and there may be others that are less important, right? Your virus checker can run once in a while. It doesn't need to be hogging resources when you're trying to detect pedestrians, right? Of course, take that analogy with a grain of salt, because sometimes you really need to have the attack detector running also concurrently with your, let's say, machine learning pedestrian detection, as we discussed last time, right? So basically, these applications exist, and some of them really require quality of service guarantees. And if you don't provide support for fairness in your system, then you have a problem. So we want the system to be controllable and high performance. You don't want to get 3x performance loss or 5x performance loss in one application, especially if that application requires some guarantees from you. Okay, now let me give you the answer. I mean, we actually did a lot of studies, and we basically nailed down the problem to the memory controller. Because in the system that we tested, L2 caches were private, so the cores did not interfere with each other in the L2 caches over here. So we have a shared memory system, and you have a memory controller over here. And let's say we're running MATLAB and GCC together concurrently. MATLAB keeps sending a lot of requests to memory. GCC sends requests once in a while because it's not very intensive. It doesn't require a lot of data from memory. And it turns out memory controller somehow almost always prioritizes MATLAB. And we basically pinpointed the problem to unfairness in the memory controller. Memory controller was somehow unfairly deprioritizing GCC. And as a result, Even though GCC was scheduled nicely by the operating system, it was using its caches, etc., its requests were not being serviced by the memory controller. As a result, it got delayed and delayed and delayed. And as a result, it got slowed down by 3x in that picture. So let's dig deeper now. Why is this happening? Why are the memory controllers doing this? And let me give you a little bit more into how each of these DRAM banks behave. How are they structured? So a DRAM bank consists of two-dimensional arrays, as we discussed also when we discussed RowHammer. Now we're going to go a little bit deeper into it. You have rows and columns. And this view of a bank is an abstraction to begin with. Internally, actually, a bank consists of many cells. So each of these cross points in the two-dimensional array is actually a transistor and capacitor, as we've seen earlier with the DRAM refresh. And there are other structures that enable access to such cells. We're going to discuss this when we talk about memory structures. So if you don't understand the low level, don't worry about it right now, because we haven't given you the low level exactly yet. But in the high level, if you want to access a row in DRAM, you need to activate it and place it into the row buffer. That's how you can access any row over here. Initially, this row buffer is empty. And if you, let's say, want to access row 0, column 0, first, you need to decode the row address. We're going to talk all about these components actually very soon in the combination logic. We're going to talk about a decoder, and you'll figure out exactly what that is, which basically activates one row. You give the row address 0, and row decoder asserts one signal corresponding to row 0. And then that row gets activated, and its data gets moved to the row buffer in the DRAM chip through the interconnect over there. Now you have the data in the row buffer, row 0. Now interesting things start happening. Now you can actually send the column address and get the column that you want, column 0. Basically, you have send this command, give me the column that I want, and column 0 gets multiplexed out from the data part. Okay, we're going to see this multiplexer also soon in the combinational logic lecture. In fact, tomorrow and next week. So you're going to know exactly how the decoder gets built and how the multiplexer gets built. So the job of the decoder is, given an address, you assert a line. You assert only one line so that the line that you want is enabled. In this case, row 0, right? The job of the multiplexer is, given an address, you want to select what you want. So here you have some number of columns. You want to select column 0, the data out. Okay, that's the idea over here. So this, so this is what we did to access row 0, column 0. Now let's say the next access from the processor is to row 0, column 1. Now what the memory controller does is looks at the row buffer. Oh, row buffer already contains row 0, so I don't need to do all of that row activation. I can just send a column command. So this is called a row buffer hit. The data is already in the row buffer. The entire row is in the row buffer. You just need to send the column command 1 and a column address 1, and the DRAM chip sends the memory controller column data data associated with column address 1. So this was a row buffer hit. It was fast, as you can see. You just send the column address. That sounds good, right? Now let's take a look at another access to row 0. We want the processor, let's say MATLAB wants to access row 0, column 85. Again, row 0 is already in the row buffer. No problem. We don't need to activate a new row. It's a row buffer hit, and we just need to send the column address, and the data gets multiplexed out by the DRAM chip and sent to the memory controller. So because row buffer hits, you have these row buffer hits, they're much faster, and you can access data much faster. Well, let's take a look at what happens when you don't get a row buffer hit. Row 0 is open in the row buffer, but the application, let's say GCC, wants to access row 1. And if it wants to access row 1, now you need to close the row buffer first. This is a conflict, basically, in the row buffer, meaning another row is open in the row buffer than the one you want. You need to first close the row, okay, which takes time. And then you need to send the row address 1 again into the chip. It gets decoded. It takes time. And then the row address 1 gets activated. It takes time. And eventually, row 1 shows up in the row buffer. It takes time. Now you're not done yet. Now you need to send column address 0, which takes time. And then multiplexer operates, which takes time. And the data comes out. So this conflict took much longer because you need to close the row, open another row, and then send the column address. As opposed to single column address sending, in the case of a hit, you're really doing 3 things, right? Okay, so this is underlying operation of DRAM, and we're going to see how this actually builds up to this GCC and MATLAB problem soon. So basically, a row conflict access takes significantly longer than a row hit access, as I showed you earlier. And current controllers actually are designed to take advantage of this fact. In fact, in single core controllers, this was the mindset. Basically, the mindset is because these row hit accesses are much faster, prioritize row hit access over the other accesses. So there's a commonly used scheduling policy called first ready, first come, first serve, which prioritizes row hit accesses over others. And all else being equal, it prioritizes older accesses over others. And it turns out both of these criteria actually lead to unfairness. But of course, this scheduling policy is good at maximizing DRAM throughput because it's really serving those accesses that take shorter, much faster, as opposed to causing row conflicts many, many times, which take much longer. It's really trying to maximize the row buffer hit rate and serve those accesses that are inherently faster earlier, so that you take advantage of an open row buffer as much as possible. So it's nice insight, actually. It's nice scheduling. But the problem is when multiple applications share the memory control, it's not nice to some applications. Because the DRAM control is designed to maximize DRAM data throughput, the DRAM scheduling policy that I mentioned to you is unfair to some applications. So if you do row hit first scheduling, you're unfairly prioritizing applications with high row buffer locality. For example, threads that keep on accessing the same row are unfairly prioritized, right? Whereas threads by nature have a lot of conflicts, row buffer conflicts, then they're deprioritized. So oldest first also is unfair because it's unfairly prioritized memory intensive applications. If an application sends a lot of requests to memory, inherently those requests look older to the memory controller, right? Because a lot of requests are outstanding. So both of these policies are actually unfair. And as a result, DRAM control is actually vulnerable to denial of service attacks. You can write programs to exploit this unfairness and cause denial of service, as we have done in this work that was published about 14 years ago, as you can see over here. We call this memory performance attacks. And let's take a look at an example of memory performance hog. This is one memory performance hog for you. What this program does is it basically initializes two very large arrays, A and B, and copies one array to another in a streaming fashion, sequential memory access, as you can see. It goes from element 0 to element 1, element 2, element 3, element 4, and we ensure that each element is large enough so that you don't get cache hits. Every access is a cache miss over here. Okay, so this is very memory intensive. So this is a bad memory performance hog. So to control for this, we basically actually created the exact same application, except this goes through the memory randomly. So here you get a lot of row buffer hits because you're basically sequencing through a row. You're accessing consecutive columns in a row. Whereas here you get a row buffer conflict at every access, almost every access, let's say, randomly, because you're basically jumping into random places in your memory space. As a result, you're not really doing any sequential access that would take advantage of the sequential layout in a row. Okay, so this is, let's say, a sister of the streaming application, but it's a sister that has very low row buffer locality because it's doing random memory access, but it's similarly memory intensive. So we ran these two applications together, and it turns out stream destroys the performance of random. And that's essentially what's happening with MATLAB and GCC, although GCC is also not very memory intensive as well. So let's take a look at it. Let's take a look at what happens when we run stream and random together. And it's going to be obvious, hopefully, based on what I showed you. Initially, let's say row 0 is open, and stream will keep accessing row 0 over and over many times. Random is going to keep accessing random numbered rows, let's say. And because stream is accessing row 0, and the memory controller is designed to prioritize accesses that hit in the row buffer, memory controller is by nature going to prioritize all those accesses that keep hitting in row 0 at the expense of accesses that go to some other row. So implicitly, the memory controller is going to deprioritize T1, which is the random access over here. Okay. Any questions? Can people hear me? By the way, I lost my other Zoom stream, so I just want to make sure people can hear me. Okay, that's good. Somehow I don't see myself on my Zoom, other computer for whatever reason. It could be because it lost charge, so I'm going to turn it off. So if you don't hear me at any point, try to shout, but I don't know how that will happen if you lose the stream also. Okay, good. So I'm going to continue. So hopefully it's clear. Basically what happened is we've designed the memory controller to prioritize row hits, and the side effect was an application that doesn't have a lot of row hits got delayed significantly. And you can do the calculations with a row size of 8 kilobytes and a request size of 64 bytes. 100 plus requests, 128 exactly, of stream are serviced before a single request of random is serviced. Okay, that doesn't sound good. Okay, now I'm giving you the problem. Now you can come up with many, many solutions to this problem, right? Unfortunately, I don't see my other screen right now, so I'll try to juggle. But I'm sure you may be developing some ideas to solve the problem that I may not be able to see at this point. But clearly, what is the right place to solve this problem? There are many, many potential places, actually. Some are better than others, actually. And you can think about that. Programmer is tough because programmer doesn't know what other application is running in the system. So system software could be one place. Compiler is tough because you're not compiling multiple applications. Hardware memory control is a good place, actually, to think about this. DRAM might or might not be a place because it could be costly. Circuits, I don't know. Yeah. So I think you need to think about it, basically. I'm not going to go and do this thinking because we don't have time. And I'm going to take a break soon, actually, after I finish this part. But again, two major goals of this course is to ask the question, why is this happening? What am I losing? And how can I solve this problem? And do it broadly across chips, right? So for example, somebody is asking, can't we use different RAM chips for different processors? That's a good suggestion, actually. And in fact, that's one of the solution directions that we propose. Can you actually partition the memory chips or memory modules, let's say, between different applications such that these applications don't interfere with each other? And the idea, actually, if you can do that nicely, it's not a bad solution. And people are employing that solution. Remember, this picture is these results are from 2006, 2007, and that was one of our proposals. So I like that proposal. Of course, it doesn't solve all the problems, right? Because it turns out you don't have enough memory channels or memory modules, but you have many, many applications. So you still need to handle this problem in the memory controller somehow. Okay. Okay, so if you're interested, you can read the paper that introduced this problem. And if you're really interested, there are further readings. So this last one, for example, proposed an idea that's very similar to your fellow student proposed, application of our memory channel partitioning. And if you're really interested, we have a lot more lectures in computer architecture. We're not going to cover memory controllers in digital design and computer architecture because we're going to cover a lot more basics. But this is to foreshadow you that the basics that we're going to cover actually are going to be very important going into the future. And in fact, actually, even more scalable chips are more vulnerable. You can see, you can do distributed denial of service on chip when you have many, many applications and when you have a network on chip. So existing systems are becoming more like distributed systems on chip, actually. And the potential of this quality of service problem becoming a much bigger vulnerability is much more important into the future. And you can watch that in this particular lecture. Okay, so again, my takeaway is breaking the abstraction layers between components and transformation hierarchy levels and knowing what is underneath enables you to understand and solve problems and essentially design better systems. The second takeaway, hopefully, will be clear. Cooperation between multiple components and layers can enable more effective solutions and systems. And that was how we started the course also. We want hardware-software cooperation. We want cooperation across the stack. Okay, so hopefully these four things are mysteries no longer. I mean, clearly we didn't go into a whole lot of depth in Meltdown and Spectra especially, but in all of these also. But I've given you the basic ideas and basic problems so that hopefully you can start critically thinking about anything, let's say, that's thrown at you that you observe. And you can start critically thinking about also solutions or more broadly thinking about solutions as well. So let me finish with this takeaway and we're going to take a break and then we're going to continue with the lab's presentation after 10 minutes. So hopefully it's clear. I'm certainly very excited, but I think in general, it's a very, very exciting time to be understanding and designing computing architectures. Many challenging and exciting problems exist in platform design that no one has tackled or thought about before, and that can have huge impact on the world's future, like sustainability. Problem is actually exacerbated today, unfortunately, because of the way we build computers. And in fact, because if you look at this huge hunger for data we have and how we are designing computers to, let's say, do machine learning, artificial intelligence, we're really consuming, let me say consuming, but we're probably wasting a whole lot of power to actually do models, to generate these models that can learn. And even then, they may not be learning very well, as we've discussed earlier, right? So basically, but we would like to do that still, but we would like to do it very, very efficiently. So today, we can easily collect more data that we can analyze and understand. The question is, how do we actually do it very efficiently and design systems that are useful for the future? And also, there are significant difficulties at the technology layer that I showed you with RowHammer, refresh, but there are other issues like energy, reliability, complexity, security, scalability. So hopefully you're motivated. We're actually still at the introduction part of the course. We're going to go into the real material with the labs today. But let me finish with this one. So I'm actually going to give you extra credit. I believe in extra credit if you actually do more. So there's a lecture video. I shouldn't say it's required. It's required if you want to get the good extra credit that it comes with. So why study computer architecture? I've given lectures. Actually, my inaugural lecture at ETH was future computing platforms or future computing architectures, challenges and opportunities. So you can watch either the 2017 version of that lecture, which is a bit outdated right now, but it's essentially the same because it's very fundamental. Or you can watch the February 2021 lecture. And I would suggest if you write a one-page summary of one of the two lectures, you can do both also if you want, you can get 1% extra credit. So basically, if you do everything perfectly in this course, you're going to get 100%. If you do this optional assignment, you're going to get 101%. So that's the bonus credit, basically. And I'd like to hear what are your key takeaways? What did you learn? What did you like or dislike? And please submit your summary to Moodle. And frankly, in my opinion, I would recommend watching the February 2021 version because you'll learn more about it. May 2017 version is an easier version of it, let's say. Okay. So this is, I took longer than expected. I was going to cover Bloom filters, but we're not going to do that. I have some slides on Bloom filters. If you're interested, you can go and look at them on your own. And we're probably going to post a video, optional, completely optional video if you're interested. But we're done with lecture 3A. Now let's take a 10-minute break. And after that, Hassan will take over and cover the labs. And feel free to keep asking questions. We'll try to respond to them somehow. Okay, so we'll be back in 10 minutes. That's 15:20 according to my cell phone over here. Okay, I think we should get started with the second part of the lecture. Hassan, are you ready?
Yes, I am.
Okay, maybe you can share your screen. You should be able to do it. Kick me out.
Yeah.
So Hassan is the head TA for the labs, and he's going to cover essentially FPGAs and the labs. Go ahead.
Yeah, I will start shortly.
Sure.
Just want to make sure that I see the chat window.
Okay.
Okay. Yeah, so in the second part of this lecture today, we will go over the lab sessions that are part of this course. And I will also show you the FPGA that we will be using in those lab sessions, and also give a general information about FPGAs. Okay, so let's first start with some logistics. So this semester, all lectures and lab sessions will be online. We will be using Zoom again for the lab sessions. We will soon share more details about exactly how we will do those. But basically, you will be joining a Zoom meeting, and we will expect you to work on the assignments during these hours, depending on like which session you have already chosen from the from Moodle. Yeah, and basically we will expect you to attend those Zoom sessions during these hours, where you can ask questions to the TAs and get help with the assignments. Yeah, and as I said, we will share more information about how this will work exactly. So I got questions about like using past year grades for the labs. So like we share the Moodle form for that, where you can choose whether you want to use your past grades or not. But I think some of you missed that. And so if you still want to use your grades, I guess you can send me an email. But so there's a deadline for that, right? So you cannot just decide that after the classes started or to the like end of the semester. So you have to decide it now. I guess like let's set like a hard deadline until like end of this week. So anybody who wants to use their past grades should send me an email until the end of the week. Okay. And so about the partners, so many of you did not like choose partners, did not indicate their partners. We will group you randomly, and we will share that information again later this week. Somebody says, I already decided, but the thing, okay. So it is like, if you have said that you want to use your past grades and you are sure that you have past grades, then it should be okay. There's like nothing to be confirmed. Only one of the partners has to fill the form for the like for telling us who will be your partner. Okay, so that form where you have like 2 names and 2 leggy numbers, only one of you should do that. But for selecting which of these sessions you want to attend, both partners should do that. And obviously, like both partners should choose the same session. And you can either work in person during those lab sessions if you would like to come together, or you can just like communicate in the Zoom meeting. Okay, I assume there are no further questions. And so in this slide, I will talk about the grading of the lab sessions. In total, we have 10 labs and 10 different assignments. You will get 30 points in total. We will be putting lab manuals online on the website. Here's the link. And the grading, you'll get graded for 2 things. First is in-class evaluation. So this is a grade you get based on what percentage of the lab manual you have completed. So you have certain tasks in every manual. So if you complete all of them, you'll get 70% of the grade of like that lab session. And 30% will come from the lab reports. You will also get instructions for that, but if you're curious, you can take a look at the lab reports of the last year. So you can get to that website from this year's website. You will see the link on the left sidebar. Yeah, so you'll be also submitting reports. So you can submit reports later than the deadline, but you will get a 1-point penalty for that. And the deadline for the lab reports will be 2 weeks after the lab session. Okay, so Matthias says, I missed the deadline for the lab enrollment. Is it still possible to do it? Yes, I guess. Just send me an email. Okay, so like we announced this earlier, you can use your past grades, and this is the model of the last year grades, and you can see your grades here. And for questions, we prefer you use Piazza because we have more control on that, and it's easier to handle. But you can also send the email to this list over here, and your emails will be sent to all TAs. Okay, so this was all about all I wanted to talk about the lab logistics. So there might be some questions about like how lab sessions will work, but as I said, we will make that clear later. We will send an announcement on Moodle, also on Piazza. But yeah, it's not complicated. You'll just need to basically attend this Zoom lecture. Okay. Okay, yeah, so let's continue with the next part. What will we learn in the lab sessions? So you have seen this transformation hierarchy multiple times in this class so far. And in the labs, we will work on like all these 3 different layers, logic, microarchitecture, and software hardware interface. Specifically, we will be designing logic gates. We will be designing circuits using logic gates. We will be adding new instructions to a processor, and we will be also writing code using the instruction sets architecture or just instructions. Okay, and yeah, so we expect you get hands-on experiments in digital circuit design and implementation, and be comfortable working on all these 3 different layers. Okay. Also, we will expect you to like learn to make trade-offs between performance and area complexity when you are designing hardware. And so in general, we will be doing a lot of hardware prototyping on an FPGA. We will work on some debugging tasks where you try to find what is wrong in the hardware design and learn how to debug these issues in the hardware. We will learn Verilog, which is a hardware description language. So this is sort of like a language we use to describe the hardware that we want to implement. So it's basically an easier way to design complex circuits. And we will learn how a hardware design flow works. And for that, we will be using what we call computer-aided design tools or CAD tools to make some of the tasks automatically. Okay, so like before going over like the lab exercises and telling you about the FPGAs, first I want to tell you where the FPGAs are used in today's systems. So first, here we have Microsoft's Project Brainwave as an example. So Project Brainwave is a deep learning platform for real-time AI inference. In this project, Microsoft is basically using FPGAs to accelerate their deep learning tasks. And you can see their prototype board over here, and we have like a bunch of links if you want to learn more. Okay, second example is Amazon is providing FPGAs, they're literally renting FPGAs in their cloud services, which you can use to accelerate your own applications. And these FPGAs are already used like for many things, including like the areas that I've listed here. Okay, so another example is FPGAs are also used in bioinformatics. Specifically, they're used for DNA sequencing, which is a quite time-consuming task. And yeah, so here's one example where you see a board that has an FPGA and a lot of memory to perform the sequencing of a DNA. There are more examples here in the bioinformatics area. So here you can see two recent works from our group that accelerate different aspects of the DNA sequencing task in general. Okay, another use case of the FPGAs is when you want to interface devices in like more flexible or different way than what the existing systems offer you. And in this example, we use FPGA to implement SoftMC, which stands for soft memory controller, or like software-based memory controller that allows us to access DRAM in like a flexible way, so we can issue any command at any time and have like a full control on like what's going on in the DRAM interface. And this is very helpful to like do research on DRAM to characterize various aspects of the DRAM and like do testing. We also have like a new version of SoftMC which supports DDR4, and this is already used in some papers that I've listed here. Okay. Yeah, so basically FPGA infrastructures enabled research into RowHammer, and basically they provide us a deep understanding of the RowHammer problem and help us develop potential solutions. And now let's look at some examples. So 7 years ago, we used like an earlier version of, or researchers used an earlier version of SoftMC to find the RowHammer issue in DRAM. And this was the paper that was published in 2014. And later, last year, we revisited the RowHammer problem and analyzed new devices, like more recent DRAM devices, and showed that the RowHammer problem is getting even more serious, meaning that DRAM devices are getting more vulnerable to RowHammer. And there's also another work called Trespass. And in this work, researchers tried to show that the mechanisms to prevent against RowHammer that the manufacturers implement today are not sufficient to actually protect against all kinds of different hammering patterns that we can do. And in this paper, they show how you can change your DRAM hammering pattern, meaning how you can access the DRAM to still induce bit flips. So there's a question, what are FPGAs? We will come to that. But basically, in a high level, FPGAs are a hardware that is reconfigurable. I'll explain about it more quickly. And okay, maybe one last example is FPGAs can also be used to interface different types of memories. And one example here is flash memory. It can be used to characterize and test flash memories and also other types of memories. And this is a more recent paper that summarizes the most recent advances in SSDs, which use flash chips typically. And yeah, so FPGA infrastructures enabled research into flash memory and SSD to improve their reliability, performance, and they provided us deep understanding of the problems in those areas and develop potential solutions. Okay, and I think this is the last example. FPGAs can also be used to accelerate various applications. Here, particularly FPGAs are used in this work to accelerate climate modeling. Yeah, and so here in this paper, if you're interested, you can learn more about how they accelerated tensile computation, which is the essential part of climate modeling. Okay, in the next part, I will go over the lab exercises that we will be doing. But first, let me introduce the FPGA board that we will be using. Yeah, so this is the FPGA board, and I will go over the components one by one. We have various interfaces that are used to get inputs and also to output something out of the FPGA. And the FPGA is what you see here in the middle. So this is the FPGA chip, and the rest that you see on this board is just some peripherals that we use to get inputs and outputs, as I said. Okay, so we have USB, we have video out, so specifically the VGA interface. We have micro USB, which we'll be using to supply power to this board and also to reprogram the FPGA. We have a power switch to turn the board on, 7-segment display, so this is like some sort of output device, and LEDs, again, to show some output in terms of like, yeah, just LEDs. So switches, we use switches to like input some data to the FPGA, and similarly, we also use push buttons as input. Okay, and finally, this thing in the middle is the FPGA chip, and in the following slides, I will talk about what is inside the FPGA chips and how we program them. So you'll get like a very high-level understanding of that, hopefully. But before that, I will go over the labs. I will try to explain what kind of tasks you will be responsible for during the lab sessions. So at the end of the lab exercises, when like we are done with all of them, you will learn how to develop a simple 32-bit microprocessor running on an FPGA board. Don't worry, it will not be as complicated as it sounds here, because we will be doing things incrementally, and yeah, you will learn it piece by piece. Okay, so each week we will have a new exercise. Not all exercises will require an FPGA board, and the first exercise is the one that will not require an FPGA board. Okay, so yeah, so you are encouraged to experiment with the board on your own, so you don't have to like only use it to do the lab assignments, but you can explore on your own and try new things. So for those who are interested to like work on the board individually, if we end up having some extra boards, we can also give some extra boards to you. So one group can get more than one board potentially, but we cannot promise that. Do we get FPGA boards? Yes, you will get FPGA boards. I will tell you how. And the last thing on the slide is it is not possible to destroy the board by programming it. So this is why we strongly encourage you to like try different things. When you're done with the lab, you can like think of like if you're not sure about like why something is working as it is, and you want to try what will happen if you change something, feel free to do that. Yeah. Okay, yeah, so maybe here I will mention how you will get the FPGA boards. We will announce some time slots in which you can come to the ETZ building at ETH and get the board. Okay, so you'll basically have, I guess, 15-minute time slots for which you will register, and one group member will need to come to the ETZ building to get the board. And we will most likely do that next week. So we'll have multiple slots and in like multiple days next week, and we will announce them later this week. What programming language do you use to program the boards? We will mainly use Verilog, but on your own, you are also free to explore other languages like System Verilog or VHDL. Yes, only one person will get the, we will give one board per group, and you will need to figure out basically how you will share that board. It is possible that okay, so you won't need the board until the very last step where you will need to test your design. So it will be okay to like if one student uses the board remotely, right? So you can potentially send your like bit file, the thing that you synthesize after implementing your design to your partner. So you send the bit file to your partner, and your partner can upload that to the FPGA, and I don't know, like you can just see what's happening from the camera. Yes, we don't need FPGA for the first lab session. You can buy an FPGA yourself. Yeah, so here in the slides, we have a link. So the board is called Basis 3. You can look it up online, and yeah, if you want, you can purchase one. but that's not necessary. Okay, I see some other questions, but I will also answer them later in the slides. Okay, so let's start with the first lab. So this is the simplest thing we can do. Like we will start very simple. We will draw a basic circuit. It will be a comparison circuit where we will learn how to compare numbers. Basically, a circuit that tells whether the first number is smaller or larger than the second number, or whether two numbers are equal to each other. So we will compare two electrical signals because we will be representing numbers as electrical signals and find whether they are the same. And the result output is also 1-bit electrical signal, right? So it's 1 or 0, or maybe if you want to indicate whether it's greater or smaller, then yeah, we may need to use more bits. So for this one, no FPGA programming is involved. We will ask you to draw the circuits on paper using the basic logic blocks, which we will learn about later. Okay, and in the second lab, we will do something slightly more involved. We will learn how to design a circuit that performs an addition operation. So this addition circuit will basically add two 1-bit numbers. And later, we will design another circuit that reuses this 1-bit adder to design a bigger adder. So in this case, it will be a 4-bit adder. So this will be basically where you will learn how to design your circuit in a modular way. Okay, and here as an input, we will use the switches on the board that I showed you previously, and we will display the output on the LEDs. Lab 3. In Lab 3, we will be going deeper on the combinatorial circuits. And yeah, we will basically learn how to display the result of the previous lab where we do the addition operation on a 7-segment display. As like you see here, we will like whatever the result of the addition is, we will display that as a number. Okay, lab 4 is about finite state machines. So like up until this lab, all circuits that we design will be combinational, which means they have no memory. So like the result always changes based on whatever inputs you provide to the circuit. But for the first time in this lab, we will implement circuits that have memories. So what that means, so in this example, you can see like a car that either has its like turning left signal on or turning right signal on, or both of them are off. So basically here you can see that we have like 3 states. Each circle represents a different state, and the arrows represent those state transitions. So in order to know in which state the circuit is, we have to implement some sort of a memory that tells, okay, this is this state, or this is the turning right state. Okay, and lab 5, we will learn a bit more about arithmetic operations and how to implement arithmetic operations in hardware. So this will be like very first step of designing a full processor. So we will extend like the addition operation with some more arithmetic operations. So as an example, in addition to addition, we will do subtraction, multiplication, comparison. We will combine all of them in a single hardware module. And in lab 6, we will be testing this ALU. By the way, I forgot to say ALU stands for Arithmetic and Logic Unit, as I said here, and it refers to a module that can perform multiple arithmetic operations, basically. Okay, so in this lab, we will you'll be testing the ALU. You'll learn how to write a test code that checks like different cases for the modules that you have developed. And in lab 7, we will go a bit higher and program the processor that we have implemented using an assembly language. Assembly language is basically programming a processor using the instructions that the instruction set architecture offers. So for example, you can see two pieces of codes here that do the same thing. On the left-hand side, you see the high-level like C-like code. And what this does is basically it adds together even numbers starting from 0 until 10, right? And here you see the assembly code doing the same. So you can see that there are like multiple, each line represents a different instruction, and each instruction has like its sort of like operation. So this add immediate represents what kind of operation this is, and also other operands as like source and destination operands, right? So what two numbers should add together and where to write the addition result. Okay, so we will learn about the assembly languages later in the course. Okay, and specifically the task that you will be implementing here, the program you will be implementing using MIPS assembly language will be image manipulation. We will be implementing a simple filter using assembly code. Okay, lab 8. So in lab 8, we will start integrating the pieces together. And I think this will be this lab will be covered in 2 weeks in total, but you will be doing different things in each week. Yeah, and we will learn how a processor is built, and we will complete our first MIPS-like processor design. And again, using assembly language, we will run a snake program, which will do something similar to what you have seen in the slide. So I can just play it again. Okay. Lab 9. On Lab 9, we will measure the performance of the processor that we have implemented and also improve its performance by adding new instructions. So previously, like in the processors that we will have until Lab 8 will not have these two operations, multiplication and bit shifting. Instead, we will be doing those operations using other instructions. But here in this lab, in lab 9, we will implement these two instructions to make things faster. Okay, to like perform the multiplications much faster than we can do with like addition, for example, by running addition multiple times. Okay. Cool. So I will keep moving, and in the next part we will discuss a bit more about the FPGAs, and I will tell you what's an FPGA finally. So this is the board again that we'll be using, and FPGA is this little chip over here. Okay, so FPGA stands for Field Programmable Gate Array, and FPGA is a software reconfigurable hardware substrate. It contains reconfigurable functions or logic blocks, reconfigurable interconnections of these functions or logic blocks. Basically, this reconfiguration allows us to change how these function blocks are connected to each other, and also reconfigurable input and output. Okay, so and when used well, FPGAs have very big advantages. For example, they provide higher performance than running your program in software on a CPU. And they also provide more flexibility of implementation than dedicated hardware or CPU. And they typically also have a shorter time to market because you don't have to manufacture any chip, but you can just get an FPGA, implement your hardware on it. And yeah, if everything works properly, you're done basically with your application. Okay, so yeah, so basically an FPGA looks something like this, where you have like many logic blocks, many switch blocks or interconnects that determines how these logic blocks are interconnected with each other, and also I/O blocks. So what we do when we say we program an FPGA is we configure these logic blocks and their connections and also I/O blocks to create the hardware that we want and map the programs that we want to run on this hardware. Okay, so yeah, as I mentioned in the previous slide, there are two main building blocks, the logic blocks, or we'll refer to them as like lookup tables here. a bit like simpler version of a logic block, I would say, and also switches, which we use to connect the lookup tables to each other. So basically, when we like zoom into an FPGA, it looks like this. We have a lookup table. We have switches here that that basically make up the interconnects. And basically, depending on how we configure those switches, the outputs and inputs of individual lookup tables are getting connected to like different lookup tables. And if you look inside the lookup table, it is basically just a few bits of memory and a multiplexer. And I will explain a bit more about the multiplexer. But essentially, what it does is it selects one of these like bits over here represented with the yellow rectangles and outputs the result. Okay, and yeah, so you can see here the distribution of these different building blocks in an FPGA chip. So majority of it is just interconnect. Yeah, so let me move on since we don't have too much time left. Okay, so and how do you program those FPGAs, or specifically, let's look at how do you program these lookup tables. So in this example, I'm showing a 3-bit input lookup table. So this means that we have 3 bits to select which of the storage bits we want to output. Okay, so yeah, basically, if this was like 2-bit input lookup table, then we should have only 4 of those storage bits, and yeah, have 2 bits over here at the bottom. Okay, and this blue thing over here is what we call a multiplexer. It chooses one of the 8 data inputs that we have over here. And this we will refer to as a data input, and this as a select input. On the next slide, I will show you an example where we will implement a very simple function and map it to this lookup table. Okay, so let me also mention how this input bits work. So this is basically as input bits that we use to select one of these storage bits, right? And these storage bits have addresses, as you can see here. And depending on what input bits, what 3 bits you provide to the multiplexer, a different storage bit or data input is selected. For instance, if all 3 bits are 0, whatever is written in this data input, it will be the output that you'll see. Okay, so let's get to the example. It will be more clear. But yeah, with 3 bits lookup table, you can implement any function that has 3 bits as an input, that gets 3 bits as an input. And hopefully you will be convinced after this slide that that's true. Okay, so let's implement a function that outputs 1 when there are at least 2 1s in a 3-bit input. In other words, we want a circuit that will output 1 when when at least 2 of the bits of a 3-bit input are 1. Okay, so how you will do that in C, I will show 2 examples. One example is basically going over the bits, the 3 bits one by one. So the input is the 3-bit input, and we AND it with 1 to only access the first bit, right? And add it to the count, which we initially initialize to 0. And later we shift the input by 1 to get to the second bit, and we perform this in a loop 3 times. And if it turns out that all bits that we go over here are 1, so that all of the 3 least significant bits are 1, the count should be equal to 3 at the end, like when we exit this loop, right? And later we have this if, which checks if the count is bigger than 1. If so, it returns 1, otherwise it returns 0. Another way of doing this is if you decode like these numbers over here, let me do that. So 0 will correspond to 0, 0, 0, right? And 1 will be like in binary format, represented like this. 2 is represented like this, and 4 is represented like this. So basically, Another way of implementing this in C will be using this switch case statement, where we just hard code all values that have 1 or less than 1 in them. Okay, and in that case, the return value will be 0. Otherwise, it will be 1. Okay, so how we implement this in hardware or in this lookup table by programming the lookup table will be more similar to the second approach in C. And we will go and basically hard code all values here that we want to be output depending on what are the input bits. So it's pretty straightforward. Since we know like the address of this like one data bit here, like 1 bit storage is this, we should set this value to 0, right? Because here we don't have 2 ones, we have no ones at all. All of the values are 0. Similarly, this should also be 0. This should also be 0. So here, when the 3-bit inputs that we provide to this lookup table are 3 or 0, 1, 1, we have 2 ones, and the output should be 1. That should be outputted in that case. Okay, so you can see that it's straightforward to fill those. Every time we see more than 2 ones, we write 1, otherwise we write 0. Okay, so like basically programming the FPGA to implement such simple circuits, it's pretty easy. But if you want to implement something very complicated or more complicated that will use multiple of these lookup tables, then things are getting real complicated because we need to also think about how to connect these lookup tables to each other. Okay, so actually I had an animation for this. Okay, yeah, so how to implement more complex functions. As I said, it is like a complicated task because like FPGAs are huge and we have many of these lookup tables and switches, and depending on the application, the circuit that we want to implement might be huge. So dealing with such complexity manually is not feasible. Okay, let me also tell you about the modern FPGA architectures a little bit. So I showed you an example of a 3-bit lookup table, but the modern FPGAs typically use some more complicated blocks, and they also use 6-bit lookup tables. But they also like use a lot of like custom hardware cores in the FPGAs. They even implement some simple CPU cores. Well, not very simple, but small, I would say. Okay, and those FPGAs also have megabytes of distributed on-chip memory that can be used in applications. So these are not, this cannot be used like as like to like program your logic, but rather as a storage only. And they also implement special purpose hardware blocks, as I said, and even general purpose processors embedded within the FPGA chip. And this is one example of such an FPGA. This is Xilinx Zinc UltraScale Plus FPGA. And you can see that it implements various blocks. It implements a memory controller to access DRAM. It implements some high-speed interfaces such as USB, DisplayPort, HDMI, and PCI, and other things. It even encrypts some special blocks to do data encryption and decryption. And here you can see 2 processor cores are also inside the FPGA. Okay, let me quickly go over the advantages and disadvantages of the FPGAs. So algorithm can be directly implemented in hardware, and this helps you avoid the overhead of using an instruction set architecture. And you can like highly specialize your hardware for the application, but in general purpose processors, that's not possible. You are just working with whatever is provided with the like CPU itself. It has low development costs compared to a full custom hardware design. It has short time to market, again, compared to a custom hardware design, but you can argue that like doing everything in software can have even shorter time to market. It's reconfigurable in the field. So if you notice that something is wrong in the design, FPGAs allow reconfiguration. So you can just change the design, fix some bugs, which is not possible on a custom hardware always. I mean, unless you design your hardware for that. Yeah, and FPGAs are useful and usable for many purposes. But it also comes with FPGAs also come with disadvantages. They are not as fast as full custom hardware design, and the reconfigurable comes at a cost. So, like to make the hardware configurable, they are paying a lot of area overhead. But on the other hand, if you are implementing a hardware for only a specific task, you may like fabricate a chip that is much smaller than the FPGA, but it can perform only that specific task. Okay, so I will also like to talk about how we program the FPGAs a little bit. So we don't have much time. I will try to go over this very quickly. So as I said, we have many of these resources that we want to use to implement our designs, and they're hard to program manually. And for that reason, we are using CAD tools, and we take advantage of high-level functional description languages such as Verilog. Okay, so this is a typical FPGA design flow. We start with a problem definition. So we decide what is the problem we want to solve, and then we implement a solution, or like we described, a hardware that will solve that problem. And for that, we either use Verilog or VHDL or other even higher level languages. So here, your task will be basically implementing the Verilog code of the hardware design, or of the design that you would like to implement. And logic synthesis, placement and routing, and bitstream generations, those will be handled automatically with the tools that we will be using. And this last step, after this last step, we will get a bit file, which is basically like a binary that you can run on the FPGA. But first you need to, well, I would say not run on the FPGA, but you can use it to program the FPGA. Okay, and for this, we will be using Xilinx Vivado. And this is how what Vivado looks like. Okay, I will explain it a bit more. I will run a short demo slightly after this slide. So yeah, Vivado basically helps you go through the design flow that I showed here. And it also has a embedded simulator that you can use to simulate your hardware design, which will help you to debug and find problems in your design. It provides drivers and graphical interface to easily program the FPGA using a USB cable. This is installed in the computer rooms that are listed here, but I guess it's not very practical to go out there and use the software. So we will suggest you to install Vivado on your own laptops. And there are instructions for this on the website when you go to the lab sessions page. Okay. Okay, so I will show you a very short demo, and this demo we will see how to use Vivado to implement some Verilog code and follow the FPGA design flow steps to download the bitstream to the FPGA and run some simple application, which is a keyboard demo. Basically, what this demo will do is when you press any key on the keyboard, it will be displayed on the terminal, and the FPGA will be the hardware piece that will basically process that information that a key is pressed. Okay, and here's the video. Hopefully I can play it. Okay. Wait, I'm not sure if you can hear it.
Yeah, I cannot hear it.
Yeah.
Maybe you can give it to your computer.
I don't know how to share my computer audio.
What if you turn like use the sound output from your computer directly as opposed to using your headphones?
Yeah, I don't know if that's gonna work because like the microphone is also like on the computer. Okay, share sound. Okay, I figured it out. Oh, actually, there might be nothing to hear. My bad. Okay, I will explain things as the video goes. Okay, so first we start with creating the Vivado project. So as we do like in like other IDEs, maybe we name our project. Here we select an RTL project, and in this step we will select the FPGA that we will be working with. So we will have this information, also the video, a link to the video on the website. So you don't need to memorize any of this, obviously. And after creating the project, we will start with adding the files. So here we won't be implementing the program from scratch, but rather I will go to this link over here where I will download the source files. And Okay, I will skip this step where I download the source files, and later we add those source files to the Vivado project. The first thing we add is we add the design files. So these are the actual hardware design that we have. And later we'll add the constraints. So constraints are basically, so these are like location constraints that tells which FPGA pin will be connected to which component on the FPGA board. So specifically here, we will connect the FPGA, the like wires coming out from the FPGA chip to the USB, because we will be using, we will be connecting our keyboard to the FPGA using the USB interface, as you will see shortly. But here we just simply generate the bit stream because like we are done with the design. We added all the source files, but obviously in the lab sessions you will need to write those. You'll basically have to design your module yourself. And here first we will power up the board. So we are connecting the board to a laptop. So this is how we program it and also how we supply power. We are turning the board on. When we first turn it on, it runs a, like whatever program is installed in its read-only memory. And we connect a keyboard to the FPGA. And I think this is all we needed for the like physical connections of the FPGA board. And the bit file is also generated. Now we program the FPGA using the bit file. So first in the step, you are searching for the FPGA. The system should detect it, that an FPGA is connected to the USB port. And yeah, afterwards, we select the, we select program device and select the bit file that we will use to program the FPGA. And okay, so the FPGA is programmed. So let's see what it does now. So we start at terminal and connect it to the serial interface. So if you don't understand what is this, it's not that important at the moment, but we just connect to the board basically to listen to data incoming from the board. And we can see the ASCII codes that, ASCII code that corresponds to each of these letters. So the first number you see here is the ASCII code of the letter of the key that's pressed on the keyboard. And the second thing you see here is just indicates that that key is released. Okay, so it's like press, and the second line indicates the release of the key. Okay, so this was the demo I wanted to show. I'm sorry that I took a bit longer than I expected, but hopefully this was useful. And the link is on the website if you want to watch this. If you want to watch this demo again. And also you can find all the slides. Okay. Any final questions? But I don't have time.
No, I think if there are any burning questions, we can take a few. Otherwise, we will leave them to Moodle, Piazza, wherever students decide to ask. Somebody is asking, is it similar on Mac OS?
So I think Vivado only runs on Linux and Windows. But on macOS, you can either use virtual machine or you can install Windows on that.
Yeah, virtual machine sounds like a good answer. There's another question. I don't know if you see it related to the license.
Yeah. I'll need to check that, but Xilinx should be providing a free license for the board that we are going to use. The license shouldn't be an issue, but yeah, I'll check and update the instructions if needed.
Okay. If you run into any issues, please let Hassan and other TAs know. This should be relatively easy to set up the board and everything.
Yeah, maybe for that purpose, Piazza is a better platform because like other students can also see that.
Exactly, and they can also help you, as we mentioned earlier, right? Some people may figure it out earlier and get to respond earlier also. Okay, well, hopefully you will have fun doing these labs. I think we're done for today. Tomorrow we will start with combinational logic. If you can do the reading on combinational logic, it'll be helpful. You don't have to do it, but if you do the reading, you will see that the lecture is based on the reading also, and you can you can go deeper perhaps. Okay, thanks Hassan for presenting the labs. And I will see everyone tomorrow.